So let's say we have a system. Let's imagine a system. These are going to get sloppy. I'm going to do my best to keep them clean. So we have a system with 3 molecules and 4 levels. And they all start in ground state, let's say. And then this is again the direction of increasing energy. And then let's say I add 2 units of energy, probably heat, whatever it is. How can adding the 2 units of energy happen? There's 2 ways. What does this look like? Someone can shout it out. What would be a possible option for putting 2 units of energy into 3 molecules? Move one of the dots to the second line. Love it. Second energy state, and the other 2 stay in ground state. Okay, and what is the other option? 2 move up to the first level. Okay, those are your 2 choices. Right? Okay, I've put in 2 units of energy. U total. Let's just check that everything looks good. So U total is going to be equal to 2, and it's going to be the sum of the number of molecules in a given level times the energy of that level. So this will be, for A, it's 1 molecule in the second energy level, plus 2 in the 0th equals 2. Or for B, this is, I have 2 in the first energy level, 1 plus 1 in the 0th. Sum them all up, they're both still equal to 2, so everything's conserved, everything looks good, I'm happy. Okay. So now let's consider the number of ways that A and B, these sort of configurations could happen. The number of ways is always, I'm asking for multiplicity. Okay. So for our A case, we could have the first molecule pops up into the second level and the next 2 stay down in the 0th, or the middle molecule is in the second energy level, okay, and the first and third stay in the ground state, or the last molecule could be the one that moves up to the second level. Okay? So multiplicity is equal to 3, and if you want to go through your factorials just to really make yourself happy, 3 factorial is the number of molecules is on the top. I have 2 of them in the 0th level, none are in the first, 1 is in the second, none are in the third. We know that these drop out to a 1, so they don't really need to be there. But this would be 3 times 2 times 1 over 2 times 1 times 1 times 1. This is 6 over 2, this is 3. Okay. What is multiplicity for B? It's not 6. Here it is again. How many molecules do I have is on the top, the energy levels, and how many are in each of them, each of the categories. Do you have a question?
Yeah, can you describe how you did the bottom history? Is that 2, 0, and 1 0?
This is 2 factorial for the 0th level, 0 factorial for the first, 1 factorial for the second, 0 factorial for the third. And like I said, going forward, you wouldn't necessarily bother to include the 0 factorials. Right? But those were for all the energy levels. okay? From ground state to the third level. So what's the multiplicity of B? 3, okay? It's also 3. So then are A and B equally likely to happen? Given your knowledge of multiplicity and entropy, what would you say? Yes. These have the same multiplicity. Okay. These would have the same entropy by our statistical definition. They are equally likely, given that we're just trying to maximize multiplicity, but they have the same. As soon as we get into bigger systems, that stops really being a concern. Again, it'll always be obvious kind of what we're moving towards. So Boltzmann's statistical definition of entropy here is sort of the best possible calculation that you can have. This is the best possible calc for entropy. Multiplicity in real life would combine both positional and energetic. Okay, so you think about where all the energy of every single molecule is and the position of every single molecule, and that's how you would decide what the maximum multiplicity is. We are not going to do that. They'll always be separate in this class. I'll only ask for one or the other. And moreover, in real life, it's impossible to track all of those things. Okay? So again, if you could actually get multiplicity for every molecule, this would be sort of like a perfect measure of entropy, but that's not real life. So what we have instead is delta S equals Q reversible over T, our classical definition. Okay. I actually wrote on my notes here, this one sucks. Maybe some better description of that would simply be that this assumption is not real, right? The reversible case really isn't true. We know that delta S is always really bigger. Okay, so the equal sign isn't super meaningful for us. And we can only do a change. We're using heat flow, so we have to do a difference in entropy. We can't get entropy for a given state with this value either, right? So it's, it's only for change. So it's just not as informative. Okay? Easier to measure. Yep.
So were you saying that like the molecules themselves are distinguishable?
Every molecule in real life would be, you could tell it apart and you would track everything it does. Okay. In some cases you might go like, oh, all of this particular protein, we could treat them equivalently, but it's different than this other one, which is different than this other one. So then what we want to introduce now is something that falls in between, okay? Something for when we have really big numbers of N, really big numbers of molecules, so it's really difficult to calculate multiplicity, it's difficult to calculate entropy. So what we have then instead is the probabilistic definition of entropy. If you look that up, if you put it into Google, the first thing that's going to come up is Wikipedia's page for information theory. If here, there it is. That's what it's built on. And the equation itself is S is equal to negative capital N, Boltzmann's constant case of B. Okay, these are being multiply this by the sum of p sub I times the natural log of p sub I. Okay? So this piece here should look a little bit like Stirling. This is built off of the same approximation as Stirling. Okay. That is the equation. The N here is the total number of objects or molecules or whatever it might be. I think the example I'm going to do next is dice rolls, so full number of dice rolls, okay, in our system. K sub B is Boltzmann's constant again. P sub I here is the probability of a given object or molecule occupying the ith state, okay? Or the ith category, or the ith energy level, right? So we've been talking about energy levels is what we care about. We'll do an example with dice where the different categories or states are, did you roll a 1, a 2, a 3, a 4, a 5, or a 6? Okay, right? Doesn't have to be energy levels, although that's what we care about more. P sub I is also equal to the number in that level over the total number, right? That's our basic definition for probability. A couple of other things that we have to, maintain. The sum from I sub 0 up to t has to be equal to 1, okay? Total probability has to be sum to 1. The probability of any given state has to be less than or equal to 1. Just total number of categories you have, okay? So it might be 4 energy states, it might be the 6 different numbers on the die that you could roll. T is total categories that you have. So then, if the probability has to be less than 1, what would the natural log of the probability have to be? What's the natural log of a fraction? It's always a negative number, right? This is going to be less than 1. Actually going to be less than 0. I don't know why I wrote it like that. The log of any fraction is negative, okay? Does entropy have to be positive? Entropy does have to be positive. Change in entropy does not have to be positive, okay? But if I have a multiplicity of 1, I have only one way of something happening. The entropy is 0. 0 is the bottom of entropy, okay? There's either no entropy or there is some. There's no negative entropy. Now delta S could be negative, right? So S has to be positive. And so this explains the function of the negative sign up here, okay? Hence, negative sign in the equation. Because this whole term right here is going to be negative. What do you need? The natural log of a fraction is going to be a negative number. Okay, this is always going to be some positive fractional value. So this whole piece, I'm summing up a whole bunch of negative things. This is a number of objects or molecules. This will never be a negative value. Boltzmann is always a constant. So I need this negative here to guarantee that entropy is always a positive value. Now, delta S can be negative for your system or your surroundings, but not both. Or at least not both at the same time. Delta S universe can't be negative. So you can have like a local change in entropy that lowers entropy for your system, but that would mean it's going to be matched by some increase in the surroundings such that the overall universe won't have a negative change.